So type 2 is proof involving divisibility. So one thing to note about each of the types is that it's always going to be an element of n. It's always going to be relating to natural numbers. So that's not going to change throughout the question for any of the types, which is great. So proofs involving divisibility is slightly different to the last type, which was proofs involving series. And we have a question that's just magically appeared. Prove by induction that 3 is a factor of 4 to the power of n minus 1 for all n element of n. So a difference here is that, well, there's no pluses, so it's not a series, so there's no adding or addition. It's not a series. Usually there's a minus sign. So when I say usually, it's not always the case. So usually there's a subtraction sign, but the big thing really is the power. So we've got a power n in this question. So power of n. And for proofs by divisibility, you'll generally always get powers of n. Maybe one or two that aren't, but most of the time it's when you have powers of n is your proof by divisibility, okay? They might say something about a factor as well, or they might say prove by induction 4 to the power of n minus 1 is divisible by 3 or is divisible by whatever the number is, okay? So what we're going to start with is, again, to prove. So to prove, and it's proposition of n. And what we're doing is we're saying 3 is a factor of 4 to the power of n minus 1. So this minus 1 is not attached to the power. It's a whole number. It's a constant. It's not a power. Okay, so the minus 1 is not a power. It's the n part that's the power. Other questions you'll have more than just the n up there, but we'll get to that bit later. Okay, so step 1 is we want to show that proposition 1 is true. So again, it's the copy and paste of the first step from the other proof involving series. Okay, so proposition 1, and we fill in 1, so 4 to the power of 1 minus 1. Proposition 1 is 4 minus 1, so P1 got 3. Okay, and we're then checking, is that divisible by 3 is 1, so it is. Okay, so 3 is a factor of 3, so proposition 1 is true. Okay, that's our step 1 there. So show that P1 is true, sub in 1 for n, kind of evaluate that, we get 3, divided by 3, which we get is 1, and we're just saying, well, 3 is a factor of 3, so it's true. Okay, so that's the step 1. Go to step 2 this time, which is our assumption. So 2. So if you don't really know your indices for paper 1, you want to do a brush up on some of the rules for paper 1, because they'd be important for this chapter. So indices will be important for this chapter, because we will be using 1 or 2 rules from indices. Okay, so assume that proposition k is true. We could say for n is k, so we'll shorten that down from before. For n is k, and we're saying proposition k, 3 is a factor, is assumed true for n is k. And then what we're doing is introducing something new. So we're saying 4 to the power of n, and 4 to the power of n, replacing it with k down here. So 4 to the power of k minus 1 is equal to, so we want it to be a factor of 3, or multiple of 3, sorry. So we want 3 to be a factor of this number that we have on the left or the right hand side. So it has to be a multiple of 3. So it's 3 times something. We don't know what the something is, so we're going to say A, where A is an element of Z. Okay? And yes, that kind of contradicts what we're saying above here, that N is an element of N, so it has to be natural multiples, but we're making the assumption of Z because it's any 3 is a factor of K, and we're assuming K is any number for the moment, and we're assuming then because of K that it's any multiple of 3. So it has to be a whole number, and we're just assuming it's plus or negative for the moment. Okay, so 3A, 3 has to be a factor of this, so 3 times something is always going to be a multiple of 3. So 3 will always be a factor of 3 times another number. So then what we're going to do is we're going to isolate the K part. So isolate, we'll say in this part, in this on left hand side, move over our 1, so 4 to the power of K is equal to 3A plus 1. So 4 to the power of K is equal to 3A plus 1. That's going to stick as our part 2. So 3 then is our prove. So prove that proposition of K plus 1 is true for N equals K plus 1, given that it is true for N equals K. So it's the same same copy and paste statement that we're making for each one. It's just that our calculations are going to be slightly different because this is now divisibility, we're not talking about series. So our assumption in the second part is similar enough. This is new. Our assumption in part 3 or our statement is the same, and then our calculation part next is going to be slightly different. Okay, so proposition K plus 1, we're saying 3 is a factor of, and we're going to fill in K plus 1 in for K. So we've got 4 bracket K plus 1 minus 1. So you're filling in K plus 1 in here like we have done before in the other questions. So 4 to the power of K plus 1 minus 1. So then what we're going to do is use our indices rules, and we're going to split up the powers. Okay, so I might make a note of that in a different colour. So use indices rules to split the powers. Okay, so if we're adding powers, what we're doing to the bases is we're multiplying. Okay, so that's page 21 in the log tables for the rules. So if we add powers, we're multiplying bases. So we 4 to the power of K times 4 to the power of 1, and then our minus 1. So we've just split this piece into the two pieces here. 4 to the power of K times 4, and we'll just make it look a bit tidier. So 4 to the power of K times 4 minus 1. And what we're doing then is we're going to take, step 2 and try and fill it into part 3. So here that 4 to the power of K and 4 to the power of K are exactly the same, and we're going to fill in 3A plus 1 in for the square down here. Okay, so replace with right hand side of step 2, and we've got 3A plus 1. It's still multiplied by 4 minus 1. So 3A plus 1 in a bracket times 4 minus 1. Multiply out. 12A plus 4 minus 1. So it's all still equal to this part here. So like all of what we're doing here is going to be equal to it. And then I'm just going to move up. So you have 12a plus 4 minus 1. I'm actually going to flip the page over. This way. So we had 4 times 3a plus 1 minus 1. We multiplied out 12a plus 4 minus 1. We have 12a plus 3. And then we're going to factor out 3 because 3 is what we want, to see. So factor out 3, we have 4a plus 1. So 3 bracket 4a plus 1. And we know then from earlier that when we multiply by 3, this is some other number. So we're going to let that be 3 times whatever this bracket is. So some random letter, b, let's say for example, where b is an element of z. Okay, so if we just go back a second there. So here we said 3 times some number is a element of z. Then we realised that it was this part here, 3a plus 1. Because 3a plus 1 is different to 3 bracket 4a plus 1, we can't have 4a plus 1 being the same as a. So it's some number that's a multiplied by 4 plus 1 gives you a different number. So it's as if we had a was equal to 2, and we've got 3 bracket 4 times 2 plus 1. So 3 bracket a plus 1, 3 bracket 9. And now this number 9 is our new letter b. So we started off with a being, for example, 2. We subbed that in and we got another number, 9. And we're saying that that new number is a different variable. That's an element of z. Okay? If you don't understand that, that's fine. Just know that once you get this bracket, you're just sticking down a different letter. So it doesn't matter what letter it is as long as it's not a, k, or n. Because we've already used n from the start. We've already subbed in k and we've already subbed in a here. Okay? K is always the one you're going to use for the, k is true, and k plus 1, that's k is the one that we're going to use for this. We like to use w before, but k is what we're using for this. It's kind of the general one. A then can change, and b can change, but k has to stay the same. Okay. Then we have our conclusion. So the proposition of k plus 1 is divisible by 3, having assumed that pk is true. And then our 4 is our conclusion. And again, we're going back to the start. We've got p1 is true. We've got if pk is true, then pk plus 1 is true. And then by induction, proposition of n is true for all n element of n. So that's our first proof by divisibility.